Hey, welcome back. So last video we started to reverse the exploitation qualification challenge from RHME3 and we had just figured out a rough plan for exploitation. So rewatch this if you don't know what's going on, but we also pick up here just where we are about to develop the exploit. And while this is about a specific challenge, the technique to get to the final shell is very similar for a lot of CTF challenges. So even if you are not doing this challenge, it could still show you some generic techniques. Remember in the last video that at the start I was already thinking of what probably our goal is going to be? So in the spirit of doing this whole challenge from the reverse, let's think about which global offset entry we could overwrite. Ideally, I would love to overwrite a function there with system, which has a string for the command to execute as the first parameter. So we are looking for another function that has a similar pattern. Some people contacted me and had issues once they got so far to have an arbitrary write and could overwrite an entry of the global offset table. But what do you do now? They tried to use rob gadgets and so forth, but most of the time, at least for the easier exploitation challenges, it's mostly enough to somehow execute binsh to get a shell. In a previous stream I did, I showed how to find a one-shot execve gadget that just calls binsh, so check that out. But another technique is to just look for a fitting function. So system takes a string as the first parameter as a command to execute. So what would happen if you overwrite puts with system? Well, then every time the program would call puts, it would actually try to execute the string as a system command. Makes sense, right? But it's not really useful, so in our case we are looking for functions that might have a user-controlled string as the first parameter. Let's see. String copy could work in some cases, or strlen or puts, but also free could get past a pointer that coincidentally points to a string. For example, if the name is freed and the parameter would be a pointer to the name string. So there are a lot of options, and of course it could break the program, so you have to be a bit smart. But I chose strlen in the end, as it's getting called on a string that is read by the user. In fact, it's reading the name input here, so that's great. So to recap, we want to overwrite strlen with system, so we can execute binsh when we enter binsh as a name. To do that, we need an arbitrary write, and the name pointer in the player structure could do that for us if we control it. We also know we have a use after free, which means we interpret a value on the heap as a pointer even though the player should be freed. So hopefully we find a way to overwrite that freed memory with data we control and thus control the name pointer. Sounds like we are almost there. We just have to find a sequence of operations where we get control of this pointer. In general, this should happen when we create some players, select one, remove some and add some again. So I just sat there for a bit and just played around with different name lengths to somehow make one name overlap with the pointer. But it kinda didn't work right away. I think that's because the modern heap uses different kind of chunks, namely fast bins and so forth, and they are maintained differently. So in many cases the malloc of a new chunk would skip the freed space, but I'm not 100% sure what exactly happened. I just suspected that must influence it. But if somebody could link me a write-up that has a better understanding of the heap and goes into that issue, I would love that. Anyway, I guess that this should be the solution, so I just have to find the correct case where the overlap would happen. And at some point I did. So it happened when I registered two players with a 32-byte long name and selected the second one, deleted the second one and the first one, then allocate a new player with 19 bytes, and when we now show the selected player, we get a segfault. I got the 19 bytes from playing around with the lens and it perfectly overwrites the name pointer. You can see the segfault happened in printf, probably because the pointer was pointing into invalid memory, which would be a success. But also you can see our debug prints before the segfault, and you can compare the state of the memory where the player was selected and still healthy and the overwritten object we now used. So you see the name of the third player we created smashed the stats and the name pointer. From here on now it's easy to write the exploit. We just have to do one minor thing, and that is defeat ASLR of libc, because even if the binary is not using ASLR, Other system libraries on an ASLR enabled system will have randomized addresses. But that's easy with the name pointer we control, because we can not only use it to write data, but also read memory when we show the player and try to print the name. So we can read a libc function address from the global offset table and then calculate offsets from there. In our case, I would like strlen, so we can take the global offset table address of strlen and use that in the name we use to override the name pointer. But let's just start developing the exploit. I am writing in it Python, so first I set up a socket to connect to port 1337. I also implemented a receive all function that reads data until no data is read in a certain time frame, so until there's a timeout. Then we can simply send the inputs that correspond to the menu selections that trigger the bug. So here, add player, name stats, select player, delete the two, and then create a third player and include the address we want to set the name pointer to. In our case, the address of the global offset strlen entry. And then we send a 5, which does show player, thus printing wherever the name pointer points to. And then we do some stuff to extract those raw bytes, because it should point into the global offset table and print the address of strlen. After that, we use the cool telnetlib trick that just simply hands over the socket to us so we can send and receive data when we type on the keyboard. And when we run it, it doesn't crash and outputs the strlen address. We can also now press 5 again to see how the player looks like. And these weird bytes here are the address of strlen, and so we extract those. Now we want to calculate the base address of libc, the address where the libc binary is loaded to. To do that, we can simply open the provided libc or your local libc, depending on if you develop the exploit locally or for the remote server, and then you look for strlen and copy the address. It's different for not ASLR binaries that have their loading address specified, but in this case, the addresses start at 0, so this is the offset inside the binary where this function starts. So when we now take the absolute address that we leaked from the server and subtract the offset, we get the address where libc starts. And then we look up the address or offset for system, and when we add this offset to the libc base, we get the absolute address of system on the server. We can run it, and there it is. That's the address of system on the server. And then we can use the edit player edit name function, which will then change the name, but the name is pointing into the global offset table of strlen, so we will override that address. Some of you might have thought that wouldn't work because you noticed a realloc on the name, but in fact the realloc only happens if the string you entered is longer than the string already stored, and the address of system is not longer than the address of strlen, so we bypass the realloc and just write to it. And now next time we change the name, we can enter, for example, binsh, and then it will call strlen on this input, but strlen was overwritten with system in the previous name change and thus executes binsh, and we drop into a shell. So now we can simply find the flag file and read the secret. There we go. Done.